at the University of Colorado in Boulder, who's working with professors Mitch Spiegelman and Jason Dexter. His research focuses on computational astrophysics, and particularly magnetized accretion flows around black holes, where he uses large-scale GRMHD simulations to study energy extraction, magnetic dynamo processes, and near-horizon physics. Prasun is also interested in the dynamics of protoplanetary disks and mass transfer in binary systems. Before joining China, he had postdoctoral positions at the Inter-University Center for Astronomy and Astrophysics in India and also at Tsinghua University in China. He received his PhD in astronomy and astrophysics from the Indian Institute of Science in Bangalore. So, Prasun, the floor is yours. Take it away.
Do I need the microphone or?
You can use this one. Oops. No.
This way.
Yeah.
Sure.
Yeah.
So thanks, Julia, for the nice introduction. In this talk, I'm mostly going to talk about how the rotational energy of a black hole surrounded by a highly magnetized thin disk can be extracted and what is its implications. So mostly I have done this work with Mitch Spiegelman and Jason Dexter at GITA. But somehow, at some instances, I will show some of the other results which I have done with my other senior and junior collaborators. Is there any pointer? Yeah, it's frozen. Okay. So regarding our current work, it is mostly relevant to two different kinds of astrophysical accreting systems. One is active galactic nuclei, other is X-ray binary. In both cases, the similarity is that central accretor is the black hole. In case of AGN, a supermassive black hole is gathering mass from its surrounding medium, while in X-ray binaries, a stellar mass black hole is accumulating mass from its companion star. Now, in the due process of accretion, the gravitational energy of the infalling material is converted into the thermal energy, and it is found in the universe, probably as far as we know, it is the most efficient means of energy conversion. And these accreting systems often harbors this nice jets which is coming out from the central engine. For example, this is for M87 for an Asian, and this is for GRS 1915 plus 105, which is a X-ray binary. Now, not all the sources or even in the same source at all the instances shows the jets. Sometimes it appears and disappears. For example, if you consider a transient X-ray binary, which shows a typical evolutionary track like this. So each point is here is the evolutionary state of that source. Now, this is a composite image, and here x-axis is the hardness, X-ray hardness, which we can roughly say is the energy of the photons coming out of it, and y-axis is the X-ray intensity. Let's say it's the luminosity. So when we are at the bottom, it's the dim source. When we are at the top, it's the bright source. Similarly, when we are to the left of this region, it shows the soft spectrum, and at the right, it shows hard spectrum. Now, most of the time, the source spends time here, called quiescent state, when the spectra is harder and it's dim. Now, suddenly something happens, it starts becoming brighter and starts following this path. As it is getting brighter and brighter, spectra becomes softer and it enters into the soft state. And after a while, after spending some time here, it again comes back to the quiescent state. Now, interesting thing happens here when the accreting system is in the low hard or hard state, particularly, it shows a jet. But whenever it crosses this vertical line, we call it jet line, the jet disappears. And our current understanding is that during the soft state, a geometrically thin accretion disk is extended to close to the black hole. And when it is in the hot state, this disk recedes away from the black hole and it is truncated to a hot accretion flow, and about which Mark will talk mostly in the next part of the talk. So you can see that whenever there is a hot accretion flow close to the black hole, we see a jet. Whenever the hot accretion flow is subdominant, the jet disappears. So it tells us that probably there is a good connection between the presence of a hot accretion flow close to the black hole and the jet. What is producing the jet? Now, Blandford and Znajek proposed a magnetic mechanism which tells us about how jet can be produced by extracting the rotational energy of a black hole. So if a black hole is spinning and there are lots of magnetic flux available close to the black hole, then the magnetic field will put a torque on the rotating black hole and it will extract energy from the black hole. And this energy will come out of the black hole in the form of Poynting energy flux. Now, if we define the efficiency of this BZ process, which is the ratio of the power emitted from this region by the rest mass energy falling into the black hole through this accretion disk, it primarily depends on two factors. One is the angular velocity of the black hole or black hole spin, which depends on the spin parameter A. And second is that how much magnetic flux is available close to the black hole. So we normalize this term by mass accretion rate, so it's a dimensionless quantity. Now, if we just gather all the information I have talked about this in the last two slides, it tells us that a good environment for producing jet is provided by a hot accretion flow saturated with the large-scale magnetic flux, like this. So this is the black hole, this is the density or rest mass density of the accretion flow, and the straight lines of magnetic field from Magnetized paper. So if I just couple of this informations, it tells us that it's a magnetically arrested disk. So this is a model of accretion flow which provides a perfect condition for jet production. Now this BZ process in this kind of disk has been studied extensively by lots of authors, and it shows that it can produce powerful jets even with efficiency more than 100%. But we are interested in the bright X-ray sources, which is supposed like where a thin disk is supposed to be there. Now, Sakura and Znajek in 1973 in their phenomenal papers showed that proposed a model of standard disk model of a geometrical thin disk, and its relativistic counterpart was given by Novikov Thorne in 1974. That's missing there, but yeah. But soon after they proposed their theory, they realized that the thin disk close to the black hole is supposed to be the radiation dominated. Now, if it is the radiation dominated, the heating and cooling rate will not be balanced as we expect in a geometrically thin disk, because viscous dissipation is generating the heat, and the heat should be radiated away instantaneously to keep the disk thin. Now, in this case, heating rate, as it's a radiation pressure dominated, goes as T raised to 8, while cooling rate is a black body, so T raised to 4. Now, if there is a departure from this equilibrium point, either this way or this way, the disk will collapse or pop up. So that makes the disk thermally unstable. But we do see them in nature. So what makes it stable? There have been theories, and one of the prominent mechanisms is strong magnetic field. If a strong magnetic field is threading the disk, it can make it stable, as suggested by Bigelman and Magnetized also performed the simulation in following. Now, if the black hole is spinning and the disk is highly magnetized, we expect that the black BZ process is inevitable. It will work there. But what is the fate of that process in a highly magnetized thin disk? So to understand that, we modified the Ethernet++ code to simulate a highly magnetized thin disk, and it has been published this year. So, but here you can ask me that what is the source of this large-scale magnetic field? I'm not answering this question in this talk, but I'll be happy to talk about this with anyone interested here after the talk, and I have done a few works on them. Now, we know that in a thin disk, the magnetic flux transport is inefficient. That's why it is hard to form a highly magnetized thin disk in numerical simulations. While in the hot accretion flow, the flux transport is quite efficient, so magnetic flux will be transported in, and it will fill up the region near the black hole. And one can easily form a hot mat. So we use this hack to form a geometrically thin disk. So what do? We first form a geometrically thick hot mat. So we start with a torus around the black hole. This torus is like a big donut extended over like almost hundreds of gravitational radii, and the black hole is sitting at the center. And we thread this torus like a colloidal magnetic field loops, like wrapping up the donut like this. So if I take a cross section of the torus, it looks like this. The magnetic field lines are depicted by this string lines, and the density is by this color. Here is the temperature, but let's not talk about it. Now, as the magnetic flux transport is pretty efficient, this magnetic flux will be vectored pretty quickly, and it will fill up the region here, and it will form a hot mat like this. Here I am showing you this side is the density. So more yellowish it is denser. Blackish it is rarer. On the left is the temperature. So more red means hotter, and bluer means colder. So what we do, we form the hot mat, and then we introduce a cooling term in the energy momentum tensor here, following Scott model. And as a result, we are removing the thermal energy from the hot accretion flow. Let's see what happens. Now we have introduced the cooling, and you can see it is getting colder, and the disk is forming around the midplane. The material is like collapsing here, and is formed in a thin mat. Yeah, now I'm stopping it. It's running forever, but the characteristic will not change much. So it is like a dense midplane surrounded by a coronal region, tenuous. It's colder midplane, again hotter region. Now, generally, how to define a man? Like generally, it is characterized by something called man parameter, which is the same thing which I showed during the Blandford's next slide. This is the normalized magnetic flux threading the event horizon of the black hole, and this is the normalized by the mass accretion rate. So it's a dimensionless number. Over the years, different numerical simulations shows that in the hot mat, if this value is above the critical value around 50 or so, we can say it a mat. In our hot phase of the simulation, for us, for a 0.9 spinning black hole, the value is around 62 or 61, I forgot. So it tells us that system attains a hot mat, and which is very similar to the earlier simulations people have done. Now, when it enters into the cold regime, forming the thin mat, the value reduces to almost half of it, like 30-ish for the 0.9 spin black hole. So this is a typical feature, and I think it has been also found by Mark in his thin disk simulations, that hot mats can support more magnetic field close to the black hole compared to the thin, geometrically thin disk. Now, we have found this situation for all spinning black hole we have studied here. So before doing that, I want to introduce some nomenclature here, something called prograde disk, which means that when the black hole spin angular momentum and the disk's angular momentum are rotating in the same direction, versus the retrograde when they are misaligned. So if A greater than 0, we call it prograde. If A less than 0, we call it retrograde. So we have studied almost 6 cases for different spins starting from -0.9 to +0.99. So you can see that prograde black holes can possess more magnetic flux compared to the retrograde one. And the red one is for the thin band cases, and for the dashed one is the magnetic flux parameter for the hot mat case. And I'm just dividing it to half so that we can put them in the same scaling. So as I showed that for 0.9, the magnetic flux parameter is almost half the value for thin mat compared to the hot mat. Here, for all spin, it almost persists. And so that's all. Yeah. Now, second thing, Blandford's Znajek process. Now, before quantitatively calculating the efficiency of the BZ process, I want to see whether we do see the presence of BZ process for the spinning black hole in our simulations. So it is thought that Blandford's Znajek process is this electromagnetic analog of the Penrose process, which talks about the rotational energy extraction in the vertical picture. Like, for example, if we bring a particle, here the person with the dumbbell, from infinity into the orbital region around the black hole, split them into two, and allow one of them going into the negative energy orbit and swallowed by the black hole, here the dumbbell, so that it reduces the uh, rotational energy of the black hole. Now, if there is a physical observer here, which is rotating at a constant radius, it will see this outgoing particle, which is in the positive energy orbit. It will leave the orbital region with higher energy compared to this energy of this particle from the energy observations. Now, if BZ process is the electromagnetic analog of the Penrose process, then a physical observer would see a negative pointing flux going in. So here, green means negative and red means positive. So a pointing flux going into the Argo region. So it tells us that yes, Blandford-Znajek process is the electromagnetic analog of the Penrose process, and we do see the presence of BZ process in our simulations. Now we have to quantify how much energy is being extracted from the black hole. To do that, again, we are calculating the efficiency. So as a function of spin, efficiency, and now each red dot here represents simulations with different spin, starting from -0.9 to +0.99. And here, this yellow band shows the theoretical prediction from BZ. Now you can see that there's a good match between the theory and the experiment in our case simulations. And here again, the prograde black holes can extract more energy from the rotational energy black hole compared to the retrograde case. And the value resides almost 10% to 55% in the studied case of our simulation of different spin parameter. Now, if we compare these results with the hot mat provided by Naran's recent, 2022 paper, you can see the efficiency in the case of hot mat is much higher. It can go as like 130%. So thin mats are less efficient in extracting the rotational energy of the black hole compared to the hot mat. Now the question is that whether the energy extracted from the black hole are near the event horizon, will this power the jet all alone? Oh, it's not working. Oh, it's working. All alone, like here in our simulation, it's defined jet as the relativistic polar region, which is really flowing out. And in this way, we are extracting energy from here. And the question is that this energy extracted here will power the jet, or it will go somewhere else or not. We calculated the jet efficiency as a function of spin, like the previous plot. Here, each red dot again is the energy extracted here. We define it at eta h, and the green triangles are the jet power calculated here and here. Now you can see that the jet power is always less than the energy extracted at the event horizon. So that means the energy, 5 minutes, okay. The energy extracted here, all the energy doesn't go into the jet, rather it will go somewhere else. We think that it is either going into the vanes here or heating up the disk. Now, if it is heating up the disk, also there is another heating mechanism from the magnetic processes. Like it will create the stresses and reconnection and other stuff. It will generate the heat. Now, we use the explicit cooling function for the thin mat, so it will allow us to calculate the radiative flux from our simulation. So here is the radiative flux as a function of R. The black line is from the simulation, and we compare it with the Novikov-Thorne model, the relativistic thin disk model. You can see there are lots of power inside this scope, the innermost stable circular orbit, which is not there in the Novikov-Thorne disk, and it will have a heavy impact in the total luminosity or radiative efficiency we calculate from the thin mat. So it tells us that if you can see that this red dashed line is the Novikov-Thorne value of radiative efficiency for thin disk, while this black line is from our simulations. So it tells us that the thin mat, which is highly magnetized, is always much more radiatively efficient compared to the classical Novikov-Thorne disk. Now the question is that most of the emission is coming from the region inside the ISCO. Now inside the ISCO, matter is like plunging. So it may be that optically thick approximation, which is valid for the thin disk, is not valid. Some material will be optically thin and there will be some non-thermal emission from those regions, and it will not give the interest to emission from the interest to region will not give us only the disk emission but also the coronal emission which you see in X-ray binaries. And that is supported by our recent calculation led by Chris Nagale in the John Hopkins. He's using our simulations data and doing some post-processing and calculating the radiative transfer calculation and doing the emission coming out from the disk. So this is the region close to the black hole within 15 RG, which is in equilibrium. And you can see lots of emission coming from the ISCO here. And the region within this black dashed line called photosphere, which is tau equals to 1 line, is that it will contribute to the disk emission, while the region outside it will contribute to the coronal emission. So you can see that most of the emissions within the ISCO are actually going into the coronal emission rather than the disk emission. Now, how it will impact our understanding of the black holes? Obviously, it will probably change the measurement of spin, because in spin measurement in the continuum method, as far as I understand, it uses Novikov-Thorne model, which assume a dark plunging region. There's no emission from the region inside the ISCO. But in our simulations, we found there is at least some emission from the ISCO. So definitely it will modify the spin measurement in these models. It has been done by Zoo for weakly magnetized disk, and we think that for highly magnetized thin disk, this calculation will change a lot. So here I stop as a summary, and my time is over, I think. Yeah.
Thank you so much for the nice talk. Any questions for Prasun? In person or on Zoom? Zoom will probably get a notification from here.
Yeah,
I have a question.
Angelo, we'll let Jack ask the question first and then we'll get back to you.
Hi, thanks, very interesting. I did want to just make the point that in soft states, we don't jet emission, at least.
Yeah.
The radio jet as a rule. So I wonder your comments or thoughts on it.
Yeah, I was just, that's why I didn't talk about it, so that anyone asked me these questions. So one is that it's a pretty good question, and we had that in mind while writing the paper. See, jet means that we get some radio emission in the soft state, but it's a pointing flux dominated jet. Now, how this pointing flux dominated jet will be converted into the kinetic power, that's a different mechanism we don't understand yet. I think it will be a good research topic, because if it is pointing flux, it will just go into infinity, we do not see anything. And second thing, what I think that whether in the bright state, that means in the thin disk, we can sustain the large scale magnetic field for a long time. Because I didn't discuss my other work. When we studied the dynamo process, that is magnetic field generation, using the rotational energy of the disk, not the black hole, it shows a continuous flipping of the magnetic field with 10 dynamical period. Now, if the magnetic fields are flipping, it will destroy the large scale magnetic field pretty quickly. Now, probably that will make the disk stable, but it may not be possible that the large scale magnetic field persist for a long time. Then we will not get a steady jet, rather we will get flickering, and which might be sensitive to the best of the radio emission, sensitive to the resolution. So, yeah.
Okay, great. Angelo, would you like to unmute yourself and ask the question? I'm also happy to read it.
Yeah, so actually that was essentially the same thing I had in mind. So I'll ask I'll ask something related, which is generally what would be then your favorite explanation for the soft state and or radio quiet AGN?
So Asian, it might be a different scenario, but because I guess Asian scenario is much more dirtier compared to the X-ray binaries, which has a cleaner environment. It's all coming from the like companion star. In Asian, it can be any source. For example, I guess if I know radio quite Asians prefer prefer a particular type of host galaxy, which is supposed to provide the magnetic flux necessary for these cases, right? So yeah, I'm not sure about this, whether I think we need some do some experiment. And given the simulation runtime, we have run it for maximum 40,000 RGBC, which is like 1 second in real time for a 10 solar mass black hole. So if we want to do it for months, I don't know how much runtime is required, so I don't know. Yeah.
Yeah.
Which is
Lots
the
of
way
us
we're
to talk
saying.
about later.
Yeah,
Thanks a lot.
sure. Yeah, sure.
Thanks, Prasun. This is very interesting. If there is a stable corona within the ISCO, I wonder where do the seed photons come from?
From the outer disk.
And then they,
Because if you see this picture, the outer disk is not far. It's like 3 RG kind of stuff for a spinning 0.9 spinning black hole, where the ISK would be around 2.36 or so. So still there is a thin disk, like which will give us the soft photon from here.
okay. All right, thanks.
Yeah.
Any final questions for Prasun?
Marcus, something. Here.
Sorry.
No, go ahead. Yeah, so you had a comparison before where you showed for a spin the amount of flux on the horizon.
Mm-hmm.
I got curious so I'm assuming that's measured total net flux threading the horizon itself.
Yes.
But instead, if you calculate the net flux threading inside the ISCO and use that as a boundary, does this flatten?
Yes, the reason is that this 5EH, if I plot it as a function of radius, it increases. And they behave differently for different spin. Like, slope of point for a plus 9 will be different from 0. So they will behave differently. But we did this calculation at the horizon because to compare with the previous studies. And probably this is the region interesting for the BZ process, because BZ power is coming very close to the event horizon, not at the ISCO.
Any final questions? No? Okay, so let's thank Prasun again.